We're asked, which of the following is true for the diffusion capacitance of a p-n junction? So we're going to be looking at our semiconductor notes. So first it's saying the capacitance decreases as the forward bias increases. Well, our capacitance, when we have this right here, we're going to actually be increasing as the forward bias is increasing. So they're proportional to each other. So it's not decreasing, it's increasing. So this is incorrect. For part B, it says the amount of charge stored decreases as the forward bias increases. Well, charge is current, which is I. So the amount of current stored should actually be increasing as our forward bias is increasing. These are proportional to each other. So we can write increases here, and this is incorrect. Next, we have the capacitance decreases as the mean transit time increases. So our capacitance, right, if it's decreasing, that means we should have some larger voltage over, we should basically, if we look at this equation, we should have some small number over a large number. That's going to get it close to 0. Well, the mean time is going to be the t. And we can see that our t is up top. So this is incorrect, because if the capacitance is decreasing, that means we would have to have some small value on top, which means that this cannot be increasing. So this is also proportional to each other, so decreases. Next we have the capacitance increases as temperature increases. And so we'll mark this off here. And this one is also false. The capacitance is not going to be increasing as our temperature is increasing. So when our temperature increases, it'll actually be decreasing. So we can do DEC here just for that. And just looking this over, we don't go too much in depth with diffusion capacitance, which is our forward bias. But since the excess carrier concentration in a forward bias p-n junction varies with the applied bias, this variation in the stored charge also looks like a capacitance. This is called the diffusion capacitance and depends on the bias Vt is equal to Kt over our Qm and the mean transit time, which is the kind of weird looking T, subscript T. We also have depletion capacitance, and that's this right here. It's very similar, and it's dealing with charge and reverse voltage. When we increase the reverse bias across a p-n junction, and the depletion region gets wider. So increasing our reverse bias, this is for reverse, again, not forward bias, there's a difference. Increasing our reverse bias, that means our depletion region is going to get larger, wider. When we reduce the reverse bias, it's going to get narrower, so it has less charge in the depletion region. Since the charge stored in the depletion region varies with the bias voltage, it's going to look like a capacitance. The depletion or junction capacitance is a nonlinear, and it'll drop as the reverse bias voltage increases. The grading coefficient m depends on how the p-n junction is made. So we have m is equal to 1/2 for abrupt step functions and m is equal to 1/3 for linear junctions. And that's really it for covering this topic of the following is true for the diffusion capacitance of a p-n junction.